In November of last year, 15 billion miles from Earth, the Voyager 1 spacecraft began transmitting a sequence of readings that nobody at the Jet Propulsion Laboratory could immediately explain. The numbers did not match the spacecraft's known systems. They did not match any celestial phenomenon in the onboard models. For 3 days, the data stream carried values that engineers described in internal communications as, quote, inconsistent with our understanding of the environment at that range, end quote. Then, on the 4th day, the signal degraded. And for a while, the probe went quiet. That is where the public story gets interesting. Because a 47-year-old machine, running on plutonium that is almost exhausted, is not supposed to have any surprises left to give us. Let me walk you through what actually happened. Voyager 1 was launched on September 5, 1977, from Cape Canaveral, originally tasked with a grand tour of the outer solar system. It flew past Jupiter in 1979, past Saturn in 1980, and then, having no more planets to visit, it simply kept going. Its sister probe, Voyager 2, took a different route and visited Uranus and Neptune. Both spacecraft eventually crossed what scientists call the heliopause, the invisible boundary where the sun's solar wind runs out of pressure and the interstellar medium takes over. Voyager 1 crossed that boundary in August 2012. Voyager 2 followed in November 2018. They are now, officially, in interstellar space, the only 2 human-made objects ever to leave the bubble of our star. Their radio signal takes more than 22 hours to reach Earth one way, which means when the ground team sends a command, they wait almost 2 full days for a response. This matters because when something goes wrong out there, you do not have the luxury of real-time troubleshooting. You send a guess, and you wait. To even receive the signal at all, NASA relies on the Deep Space Network, a trio of giant radio antenna complexes spaced roughly equally around the planet in California, Spain, and Australia. The antennas are so large you can park multiple houses inside one of them. They listen continuously for a carrier wave that, by the time it reaches Earth, is weaker than the static from a cell phone at the far end of a stadium. The engineering required to pull that whisper out of the cosmic background is itself a kind of daily miracle. If the Deep Space Network ever had to be retired or rebuilt, the Voyager mission would effectively go dark regardless of whether the probes themselves still had power left to transmit. Now, Voyager 1 has had problems before. In November 2023, the probe began sending home what looked like digital gibberish. Instead of the usual telemetry, the spacecraft transmitted a repeating pattern of ones and zeros that made no sense. Engineers eventually traced the fault to a single chip in the flight data subsystem, one of the oldest computers still in active operation anywhere in the universe, running on roughly 69 kilobytes of memory. Less memory than a single modern photograph. A team at JPL spent months writing new code, breaking it into small chunks, and beaming it up to the probe. They managed to rewrite around that bad chip. By April 2024, Voyager 1 was talking clearly again. It was by any engineering standard, a miraculous save. But the signal that came through in late 2024 was different. The spacecraft was communicating clearly. The onboard systems all reported healthy. The issue was not that the data was garbled. The issue was that the data made sense, and what it said was strange. According to the information released through NASA's public updates and discussed at a planetary science meeting earlier this year, the plasma wave instrument began registering oscillations in the surrounding medium that did not fit the expected background of the local interstellar environment. The magnetometer logged brief, localized fluctuations in the magnetic field direction. The cosmic ray detector recorded a short-lived dip in particle flux. All 3 of these readings taken together suggested the spacecraft was passing through a region of space with properties that the current models did not predict. Then the signal went quiet. Not lost. Quiet. Reduced strength. Intermittent packets. For a period of roughly 72 hours, communication with Voyager 1 became degraded enough that the Deep Space Network reported difficulty locking onto the carrier wave. Eventually, the link stabilized and full telemetry resumed. But the data from those 3 days has been described by more than one mission scientist as, quote, the most unusual continuous stretch of readings we have received from either Voyager probe in the past decade, end quote. Now, scientists are not worried in the sense that tabloid headlines would have you believe. Nobody at JPL thinks Voyager 1 encountered an alien object. Let me be clear about that up front. The word worried, which appears in a lot of online coverage of this event, is doing a lot of heavy lifting. What the engineers have actually expressed is concern. Concern that the spacecraft's power is failing faster than projected. Concern that the heaters keeping the instruments warm enough to function are about to run out of juice. Concern that we may lose the probe entirely within the next year or two and not fully understand what it just showed us before that happens. That is a different kind of worry than the one the internet has been pushing. Still, the readings themselves are genuinely interesting and they deserve a careful look. The interstellar medium is not empty. Space out there is a thin plasma of ionized hydrogen laced with cosmic rays, structured by a galactic magnetic field that was compressed and warped by our sun's heliosphere before Voyager pushed through. When Voyager 1 crossed the heliopause in 2012, it entered a region where the plasma density jumped noticeably. Instruments have been measuring a slow, steady increase in that density ever since, which actually makes sense. As the spacecraft moves further from the sun's protective bubble, the ambient medium should get a little denser and a little colder. What the recent readings showed was not a smooth continuation of that trend. It was a short spike followed by a trough, followed by a return to the expected baseline. It looked to the researchers analyzing the data almost like the probe had crossed the edge of a structured pocket of plasma, a knot in the interstellar medium, a local feature that existing maps of the region do not include. Could that be a natural structure? Absolutely. The interstellar medium is full of these. There are dense clouds, low-density voids, filaments shaped by ancient supernova shockwaves, and magnetic flux tubes that extend for light years. The region Voyager is currently traversing lies near the edge of what astronomers call the local interstellar cloud, sometimes nicknamed the local fluff, which itself sits inside a larger, hotter region called the local bubble. The boundaries and internal structure of these clouds are not well mapped, because the only way to map them directly is to fly a probe through them. And we only have 2 probes doing that, and they are both running out of time. So when Voyager 1 logs a brief anomaly in plasma density and magnetic field, the boring, most likely explanation is that it crossed into and out of a small-scale structure that nobody has ever measured before because nobody has ever been there. That is not a disappointment. That is the whole point of the mission, to find out what the medium actually looks like. But a few details in the data have made researchers pause. First, the timing of the signal degradation. The communication issue began roughly at the end of the anomalous reading period, not during it. If the degraded link were caused by a random hardware issue on the spacecraft itself, you would expect the timing to be unrelated to what the instruments were measuring. The fact that the signal got weaker right after the probe cleared. The anomalous region raises the question of whether the plasma environment itself affected the transmission. Radio waves can be refracted, scattered, or delayed by passing through regions of dense ionized gas. It is possible, and some mission scientists have privately suggested this, that Voyager 1 passed through a plasma structure thick enough to briefly interfere with its own radio link back to Earth. Second, the magnetic field behavior. The direction of the interstellar magnetic field, as measured by both Voyagers, has been surprisingly consistent since the crossings. Models predicted a sharper reorientation when the probes left the heliosphere, and the data did not fully cooperate. One theory is that the Sun's magnetic influence extends further beyond the heliopause than anyone expected. The recent readings showed a brief but distinct local rotation of the field vector, which some researchers have described as either a wrinkle in that extended influence or a small magnetic cloud drifting through the region. Nobody has committed to an interpretation yet. Third, the cosmic ray dip. Galactic cosmic rays are high-energy particles that originate from sources across the Milky Way. Voyager 1's detectors have been registering a fairly steady flux of them since crossing into interstellar space. A dip in that flux, without a corresponding solar event that could have temporarily deflected them, is unusual. One explanation is a small magnetic structure briefly shielding the probe. Another is an instrument glitch, though the other sensors would not normally show correlated behavior for a random glitch. There is also a fourth strand in the data that has received less attention but is arguably the most intriguing. The onboard plasma wave subsystem, which listens for oscillations in the surrounding ionized gas, reportedly recorded a brief burst of higher frequency chatter during the anomalous window. These kinds of plasma wave events are familiar in broad strokes. Voyager has detected them before, most notably in 2012 and again in 2017, when the probe passed through what scientists called interstellar plasma oscillations triggered by distant solar disturbances. What made the recent burst unusual, according to the analysis summary, was its short duration and tight frequency band. It did not look like a shockwave from a solar event propagating outward. It looked like a more localized disturbance. Whether that means Voyager passed close to a small plasma cloud, or whether it crossed through the wake of something else entirely remains open. These three data points, taken together, give you a picture of a probe passing through a small region with its own plasma, magnetic, and particle environment. That is, in scientific terms, a new thing. Or rather, the first direct measurement of something we had only ever theorized. Now, the skeptical view. Not every scientist agrees that these readings are meaningful. Dr. Edward Stone, who served as Voyager's project scientist for 50 years before retiring in 2022, has long cautioned against over-interpretation of individual data spikes. Spacecraft instruments age. Voltage reference points drift. Timing clocks slow down. Some of what looks like a physical anomaly may simply be a side effect of 47 years of exposure to interstellar radiation on electronics that were designed in the 1970s. The engineers who built Voyager, Stone often pointed out, did extraordinary work. But no spacecraft this old has ever been this far from home, and the error bars on what counts as, quote, normal behavior, end quote, are getting wider as the mission continues. Other researchers have noted that the correlation between the anomalous readings and the signal degradation could easily be coincidence. 47 years of continuous operation produces a lot of statistical outliers. If you look hard enough at any long dataset, you will find stretches where multiple instruments happen to misbehave at the same time. That does not necessarily mean the environment caused it. The most likely truth, as usual, sits somewhere in the middle. Voyager 1 probably did pass through a small, unmapped plasma structure. Its instruments probably did register real fluctuations. The subsequent communication issue was probably a combination of environmental interference and aging hardware that were primed to have trouble at the same moment. Nothing exotic. Nothing alien. Just the boundary between human engineering and deep space, where the two do not always agree on what is happening. And yet, even the boring version of this story is remarkable. Think about what we are actually doing. A machine built before the personal computer existed, with a computer weaker than a modern microwave, is sending us measurements from a region of space no human instrument has ever sampled. It is telling us the plasma is doing something we did not expect. It is telling us the magnetic field has a wrinkle where we thought it would be smooth. It is telling us the cosmic rays dipped when nothing in our models said they should. And it is doing all of this while running on less than 4 watts of power, in temperatures that would freeze most electronics into uselessness, at a distance where its own radio signal takes nearly a full day to reach us. Most of Voyager 1's instruments have already been turned off to conserve power. The cameras went dark decades ago. The lost photograph the probe ever took, the famous pale blue dot image of Earth as a single pixel in a sunbeam, was captured in 1990. Since then, it has been flying blind in the visual sense, navigating by memory and logic alone, sending back only the readings its most essential scientific instruments can still produce. In 2025, engineers began shutting down even more systems, including the cosmic ray subsystem on Voyager 2 to extend the mission by another year or two. Voyager 1 is on a similar path. The probes are being slowly, carefully put to sleep, one function at a time. The logistics of those shutdowns are quietly astonishing. Every command has to be tested in simulation on the ground, queued into the spacecraft's tiny memory, executed without human supervision, and verified only after the signal returns a day later. A single mistake, a misfired command, or a misread telemetry packet could turn an aging probe into a dead one in an instant. The engineers managing this process describe it as the slowest, most delicate form of triage in the history of spaceflight. They are trying to preserve a patient who has already outlived every prognosis, using a medical chart written in languages most of them were not alive to learn. The original flight software was written in a specialized assembly language almost nobody uses anymore. Much of the institutional knowledge about how to navigate these systems lives in retired engineers' notebooks and in the memories of a shrinking circle of specialists. The recent anomaly is, in that context, a gift. A final postcard from an instrument that is running out of pages. Whatever it saw out there, we are not going to get a second look. If we do not understand the readings now, we may never understand them. No replacement probe is on the way. The successor mission concepts, such as interstellar probe, studied by the Johns Hopkins Applied Physics Laboratory, are still in the planning phase. Even if one launched this decade, it would take another 20 years to reach the same region of space that Voyager is in today. The data we have is the data we have. Which brings us back to the worry. The worry is not that something is out there. The worry is that the machine is almost done, and we are only just starting to see how much we do not know about the medium between the stars. Voyager 1 is scheduled to lose contact for good sometime between 2027 and 2030, when its power drops below the minimum required to run a single instrument. After that, the probe will continue drifting outward in silence, at roughly 38,000 miles per hour, for tens of thousands of years, carrying its gold-plated record of Earth's sounds into the dark. The strange data from November is, in a real sense, a warning shot. It is the universe saying, here is something you did not expect. And by the way, you are almost out of time to figure out what it means. Scientists are continuing to analyze the readings. The team at JPL has ruled out several trivial explanations and is now modeling whether the plasma structure Voyager appears to have crossed is consistent with a shockwave from a distant supernova, a magnetic flux rope, or something else entirely. A paper is reportedly in preparation. It will not settle the question. It will most likely open several new ones. A few researchers have also pointed out that Voyager 2, which is traveling in a roughly different direction through the interstellar medium, has not yet recorded a similar anomaly. This is actually useful information. If whatever Voyager 1 crossed is a localized structure, then you would not necessarily expect both probes to encounter it. They are exploring separate paths through a region no map fully describes. But if Voyager 2 in the coming months or years begins logging its own strange signatures, researchers will be able to compare timings and signal characteristics to triangulate, loosely, where these small structures live. It would not be a detailed survey. It would be 2 points of data in a vast volume of space. Still, 2 data points are better than 1, and for an environment this unexplored, better than 1 is a lot. For the rest of us, there is something quietly moving about the whole situation. A spacecraft older than most of the engineers now running it is, at the very end of its life, whispering back a mystery. It is not the dramatic first contact narrative that the internet sometimes wants it to be. It is something more human than that. It is a reminder that the space around our star is bigger and stranger than we know, and that the old machines we sent out, built by hands that are mostly gone now, are still teaching us. Whatever Voyager 1 drifted through last November, the probe is past it now. The signal is back. The readings have returned to baseline. The mission continues for a little while longer. And then, somewhere out in the dark between the stars, a machine built by people who will never know how the story ends will go silent, carrying its final observations with it. Maybe we will understand what it saw before then, maybe we will not, but the fact that it saw anything at all, this far from home, is a small miracle in itself.